Hello, we are Team 25078 for the AZ Water Student Design Competition under the Chemical and Environmental Engineering Department. This is our senior design poster that includes our introduction, alternatives analysis, the membrane bioreactor technology that we are recommending for this site, wastewater plant expansion, the site layout, economics analysis, and of course, our conclusions. This is our team that is composed of chemical and environmental engineering undergraduates.
And for the Arizona Water Association Student Design Competition, we were tasked with proposing an upgrade to the SPA-1 water reclamation facility in Surprise, Arizona to increase the capacity from 12.8 to 16.3 million gallons per day. This would be done in one of two ways, by improving plants 4 and 5, or by the addition of a sixth plant. The team evaluated 4 treatment trains, a membrane aerated bioreactor, MABR, a membrane bioreactor, MBR, a modified Lutzak-Ettinger, MLE, and finally a 4-stage Bardenfeld. All modeling was completed in the software BioWin, and all of our calculations were completed in Excel. The MLE utilizes one anoxic tank followed by one aerobic tank. While this did meet our effluent requirements, it took a significant addition of methanol, as well as those 2 tanks were huge, with one of our requirements being to minimize the footprint. This was clearly out. We did not finish optimization of this 4-stage Bardenfeld because it was already getting large tank sizes and would likely need an addition of significant amount of methanol dosing. The MABR required significant energy use to aerate the membrane. Therefore, our winning solution was the MBR.
To determine the most appropriate alternative, we developed a weighted decision matrix based on 4 criteria: water quality, capital cost, area management, and operational costs. The membrane bioreactor scored the highest overall, primarily due to its excellent effluent quality and minimal footprint. Both MLE and 4-stage Bardenfeld had lower capital costs, but their biological processes alone were not sufficient to meet effluent targets. They required significant chemical additions like methanol and alum, which drove up their operational costs. MABR offered strong treatment performance, but suffered from higher capital and electrical demands due to its hybrid aeration system.
This is our recommended design solution. To plants 4 and 5, we added membrane bioreactors in the aerobic section for the second oxidation tanks. These MBRs allowed us to combine a suspended growth biological reactor with physical filtration to make the most of the space we were given. Membrane pumps were also added before the oxidation ditches for both plants 4 and 5. Methanol and ammonox bacteria are added to the water before it enters these oxidation ditches. Methanol is used as an external carbon source to meet soluble cod demand for denitrification to occur. This effluent is currently meeting all regulatory standards. Before we landed on a recommended design solution, we went through many iterations to optimize the process. This is the first solution we tried, and obviously the nitrogen and phosphorus are very high. For optimization, we tried adding a membrane pump, adding ammonia, adding methanol with no aeration in the first tank, adding methanol with aeration in the first tank, adding more methanol, trying a bioreactor with media in it, adding ammonox and methanol, which helped, but at first made the nitrogen to very low, but the phosphorus was not low enough. So we had to balance the dosages before we hit a final conclusion. This table shows our preliminary equipment sizing for the recommended design solution. As we chose to modify plants 4 and 5, all tanks will remain the same size. Both membrane pumps and the amount of energy they use, which is around 2.6 kilowatts each, is shown in the pump section of this table. To begin our construction sequencing, approvals and permits will be obtained. Then site preparation, including rerouting the existing utilities, will happen. After that, cast in place concrete tanks for the membranes, access walkways, permeate pump stations, and associated piping will begin being constructed. Chemical storage and a dosing building will also be constructed in the proposed chemical storage purple box.
For the hydraulic profile, we had 2 major components: frictional and minor head loss. Using the pipe diameters, elevations, friction factor, and flow rates, we were able to calculate the frictional and minor head loss, which got us the total head loss with all the process units. We can see that the total system head loss calculated was 7.75 feet, and we calculate the total drop at 12.08 feet, which was the difference between the effluent discharge and influent pump station water surface elevations. And the total head loss being less than the total drop gave us the green light that this site was able to maintain its gravity-fed system. And with the hydraulic profile sketched out here, you're able to see on the bottom that the highlights of the actual changes we are creating, with no major changes besides the addition of Animox, methanol, and the membranes, and the membrane pump due to industry standards.
And now we move to the economic section. On the right-hand side, you'll find the pie chart that summarizes our capital costs. You can see that the largest portion of our capital cost, about 69%, is dedicated to the membrane modules and system. Headworks and pump systems make up the remainder, 21% for headworks and 10% for the pump systems. On the left-hand side, you see the operational and maintenance costing summary. Chemical dosing is the most significant expense, making up 37% of annual cost due to the use of methanol and Animox for nutrient removal. Maintenance falls at 32%, covering membrane replacement and general upkeep of the system. Electrical costs, estimated through Bio simulations and current facility electrical expenses, contribute to 19%, while the rest, 12%, is account for labor. Here, we're looking at the annual cash flows across an 8-year life cycle for the MBR system. Year one includes our full capital investment, and revenue begins in year 2 from the sale of reclaimed water to both residential and industrial users. Resulted in an annual depreciation value of about $4 million. As you can see in the table, the project generates steady net earnings over time, and using a 5% discount rate, we calculated the cumulative present value and achieved an IRR of about 15%.
So our conclusion is we went with the membrane bioreactor technology, with nitrogen and phosphorus being our biggest challenge to meet within the limits, but we ultimately did conclude with meeting those limits.
And since we're only altering plants 4 and plant 5, we are not adding any significant changes to the current footprint. We just need to add the membrane pump and the chemical dosing storage building.
With our hydraulics as well, we were able to maintain the site, keeping its gravity-fed system, with the only addition being the membrane pump, of course.
As of for the costing of the project, our final capital cost value comes to about $32 million, and the annual operation and maintenance fees are around $13 million, and this achieves 15% IRR, which makes the project financially viable to move forward.
These are our references. Thank you
Thank you very
for seeing our presentation.